Welcome back. This week we are looking at Labs 12 and Labs 13. And the first one we'll be talking about today is Lab 12. So that's going to be exercise 18 in your lab manual, starting on page 105. Feel free to read along. A lot of the additional information that might help to have this make more sense to you is going to be located in that lab manual. So specifically, we are going to be looking at mid-latitude cyclones. We're going to be talking about what that is. And so before we dive into the nitty-gritty of what a mid-latitude cyclone is, we are going to start by understanding a little bit more about weather and the difference between the different types of fronts that exist when warm or cold air, basically whether different air masses are moving around the world. So in its most basic form, a front is going to be that boundary zone between unlike air masses, right? And so this is the critical component. So for the most part, because it's an unlike air mass in its simplest form, we can think of it as a cold air mass and a warm air mass. And remember that this is only relative to each other, so there doesn't have to be an incredible temperature difference between the two. It just means that one air mass is going to be cooler than another air mass, which will be warmer. With that said, though, obviously there can be massive temperature changes or differences between the two, and when those temperature changes are large, that's when we can get pretty intense storms that come as a result of that. So for the most part, a front is going to be where we have these different air masses, these unlike air masses, that kind of change and interact with one another. So when we take a more extreme approach, it's when that cold polar air and warm tropical air masses can collide. Again, bringing that really cold air down from the polar regions. If we're talking about the northern hemisphere, which I'll be referring to the most part. So cold air coming down from the North Pole and warm tropical air coming up from the equator. When these collide, this creates a great example of two different fronts, a cold front and a warm front, interacting with one another. There are four types of fronts that you'll need to become familiar with. We'll take a look at an image of this in a minute. But a cold front and a warm front, again, are these main ones that we'll be looking at, as these are the advancing fronts. This is advancing cold air or advancing warm air. And what I really need you to pay attention to is pay attention to how these different fronts are designated on a map. So not only can we or should we be paying attention to these colors, generally blue is going to be cold, red is going to be warm, but if we're ever looking at a black and white map, what you really have to pay attention to are the peaks. So a cold front is always going to have like this little mountain part, and a warm front is going to have this half circle. A stationary front is neither air mass is advancing, so the cold front and the warm front are just kind of hanging out together. And so that stationary front gets marked on a map with this interchanging cold, warm designation, showing that they are just hanging out next to each other rather than advancing. And an occluded front is when the cold front eventually catches up to the warm front. This will make sense on the next slide. But that is going to be designated by this change, not only change in color on most maps, but again, most importantly, that symbology, that all of the little symbols, the peaks and the half circles, are going to be on the same side of this line, meaning that the, again, cold front has caught up to the warm front. Let's take a look at how the cold front and warm fronts interact with one another, as this is going to be most prevalent when we're actually talking about mid-latitude cyclones. So a cold front, again, is that advancing cold air mass, which is going to displace the warm air mass, basically displacing warm air. Cold air is going to be seen as a wedge, diving back down to this image. So you can see that this diagram is attempting to show this cold air parcel moving horizontally across Earth. And this is basically causing a wedge. And as the cold air is moving along Earth's surface, it is forcing the warm air to rise above it. Typically steeper and faster moving than warm fronts. So again, when we talk about steeper, we're also talking about that air pressure and the density. And we learned previously that when you have air masses where the air pressure gradients is closer together, then that means we know that the air is moving faster, the wind is moving faster. So a cold front is typically moving faster than a warm front, and that is forcing the warm air to rise. That is more rapid lifting. Adiabatic cooling, we also just learned what that is, right? That is the cooling of the atmosphere not due to a change in heat, but due to the expansion of the air parcel. So there are more and more dense air parcels lower to the ground, and as that air parcel rises up into the atmosphere, it is going to expand due to air pressure and density, and that is going to force that cooling. And so when that happens, we know that the atmosphere becomes unstable, right? It is less stable as that air is rising up, and that is going to not only be associated with gusty, violent storm weather, as all of this warm, moist air is being forced up into the atmosphere. We reach that LCL, that lifting condensation level, where we have that immediate dew point, clouds form rapidly, and this can result in heavy precipitation. So the cold front, as it moves across, forcing this warm air up, all of that moist air rises, cools through the adiabatic process, and this can result again in those gusty, violent storm weathers that can result in heavy precipitation. So on the other hand, a warm front is an advancing warm air mass that overrides the cold air mass. So it is, when you compare it to the cold air mass, the warm air mass is a gentle slope of warm air that rises above the cool air. So again, diving down into this diagram, you can see that the cool air is hanging out underneath the warm air. And even though the warm air is moving from left to right, we're looking at this as the trailing edge of the warm front. So you can think of this as the last section, again, where that cold air is located, because this line is also going to be moving from the left side of our screen to the right. So it's the trailing edge of warm. So everything behind it is warm. But the interaction that we see is that the adiabatic cooling is much slower because it is not being forced up by that rapidly moving cold air front. So clouds and precipitation are still prevalent, but critically, they are nowhere near as violent or extreme as when you have a cold front forcing warm air to rise. So clouds and precipitation often extend much further ahead of the level front boundary or the ground level front boundary, and that is just because in these areas you already know that the warm air is rising up in the atmosphere. There's still going to be some moisture in this warm air that is moving from the left to the right, and as that rises up into the atmosphere, we're still going to experience some of the adiabatic cooling. So that means that there is still a good chance of not only cloud formation when we reach that LCL, but also moderate precipitation. But okay, so we talked about warm fronts, we talked about cold fronts, but what does this have to do with a mid-latitude cyclone? Taking the globe into consideration, if we have our tropics, right? This is our equator down here. And if we go up or down in our latitudes, we have at the northern point, we have our North Pole and our southern pole. So the mid-latitudes is literally this region of latitudes that is basically between the North Pole and the equator. So our mid-latitudes is this area right here, and this is where we're going to find our mid-latitude cyclones. So the reason that we talk about mid-latitudes is because they are an area where there is generally a lot of conflict between different air masses. The tropics typically have that warm air that is moving northwards, while the polar regions have the cooler air moving southwards. And in these mid-latitude regions is where we're going to have a lot of these atmospheric disturbances. Localized weather, again, can be incredibly severe. That is when that really strong, fast-moving cold front comes down over, again, if we are just looking at North America, comes down over the northern half of the United States, down through Canada, and forces that warm air up, creating intense storms, thunderstorms, and even sometimes tornadoes. So when we talk about mid-latitude cyclones, we are talking about the storms that happen generally over these large continental areas where we're having this conflict between the warm air masses that are coming up from the tropical and subtropic regions interacting with the cold air coming down from the North Pole. And so when we talk about a cyclone, it's also really important to note that while a cyclone, people use the term cyclone for severe storms that can happen over the ocean. I feel like people often use them hand in hand with something like a hurricane, but there is a difference between this. So mid-latitude cyclone specifically is going to be these two air masses coming into conflict over a continent. And so it's also a cyclone because the air masses are generally spinning in a counterclockwise direction, right? Clockwise goes from the left side to the right side, and counterclockwise is going to be spinning in that opposite direction. Again, a mid-latitude cyclone will only spin in a counterclockwise direction in the northern hemisphere. In the southern hemisphere, so south of the equator, it would actually be spinning in the opposite direction. So a mid-latitude cyclone is a large, migratory, low-pressure system. So it is an expansive system. As you can see here, this system right now is covering the majority of the United States. And importantly, we have a low-pressure system in here. A high pressure system is going to exist somewhere else, and so a low pressure system, again, is in general, you can think of it as the air being sucked up into the higher atmosphere, while a high pressure system is air coming down through the atmosphere from the upper atmosphere down to Earth's surface. So all of this air is basically being funneled in towards this low pressure system before it be surface level air, before it gets sucked into this low pressure system and rises up in elevation. So when we have a cold air mass and a warm air mass that converge, it is going to divide the cyclone into a warm sector and a cool sector. And the cool sector is generally larger at the surface, while the warm sector is more extensive aloft. So this is referring to the upper atmosphere. And it's also important to note that the cold air mass is generally always moving faster than the warm air mass. So if we are in a cold front and a warm front that is spinning in a counterclockwise direction, again because we're in the northern hemisphere, eventually this cold air mass will catch up to the warm air mass, and that will put an end to the mid-latitude cyclone. And how do we know that? If we jump back up to the top here, we can see that the four types of fronts. That one front is the occluded front, which is when the cold front catches up to the warm front, and that's where we're going to end up with this distinction. So the mid-latitude cyclones has a cold front catching up to the warm front. The cold front is forcing warm air to rise quickly, causing storms. If this cold front is moving at an incredibly rapid rate, this can cause, again, tornadoes. And because it is a mid-latitude cyclone, they generally occur between 30 and 70 degrees latitude. So again, we can see that displayed right here on this map, 30 degrees north, 50, so 70 degrees north is going to be up here somewhere, and that is why we call these mid-latitude cyclones mid-latitude cyclones. This is the same image, but basically focused in on this cutout so that we can see this again. Again, showing how the cold air mass is pushing its way through. We have the cold front that is catching up to, again, what is referred to as the warm front, but this is more or less the trailing end, of the warm front. And again, paying attention to the different types of weather events that are occurring based off of the cold front and the warm front is crucial to understanding what you need for this lab. So again, please look at exercise 18, mid-latitude cyclones in your lab manual. There is another great image which I don't happen to have on my PowerPoint here. It's figure 18-2 that shows you the stages of the mid-latitude cyclone. You know, how the warm front and the cold front are spinning and how the cold front catches up to the warm front, and then how that transitions through until the storm comes to an end when we get to the full occlusion, which happens after the occluded front. So please review the information in your lab manual, take a look at the practice exam, and let me know if there are any questions. Thanks.